Hi everyone, I'll be presenting the work I did for CS Plus over the summer on continuous distribution on orientation, interdomain orientation. So to begin with, I will introduce different types of interdomain motion distribution, and then I will introduce the Bingham distribution. For the method I was working on over the summer, which is the gradient descent method, I will introduce how I initialize the gradient descent and also present the result and validation. As we know, the shape of a biomolecule especially will determine their function, and they're flexible in the solution. And part of the reason why is because they might have different domains connected by flexible linker. So one domain can basically rotate around the other domain via this linker, and they are still connected to each other. So in order to model this interdomain motion, previously people use some kind of discrete model, which is basically creating several models and assign probability to each of them. Like for example, this one might have a probability of 40%, this one has like a 20%. You get the idea. And however, they suffer from some drawbacks, meaning they tend to overfit and require some physical assumption that all the other states have a probability of 0. And to overcome these issues, I'm using some kind of continuous model. So basically, instead of generating a bunch of different models and there's some probability, I will use some kind of probability density function, P, to model the interdomain orientation. And in order to find the continuous model, we can start by measuring the Sorbet tensor or something that informs us how the domain orientate itself in the solution. And via the property of the Sorbet tensor, we can get this following formula, which says the orientation of the first Sorbet tensor is related to by the second or Sorbet tensor of the second domain by some kind of a rotation. And in a solution, we can only observe the average version of this this formula. So that's where the integration came from. And if we have the correct interdomain motion model here, then we can perfectly recover the motion of the second Sorbet tensor from the first Sorbet tensor. And so, it's pretty. At this point, we can generate the objective function for our goal, which is to basically generate a distribution that can best predict the second Sorbet tensor from the first Sorbet tensor. And the distribution I was working with mostly over the summer is called the Bingham distribution. So it basically can be thought of as a downward distribution on a sphere. And the reason why I chose a distribution on a sphere is because the one representation of a rotation matrix is called quaternions, and they lies on the S3 sphere. So basically, it's a unit sphere in a 4-dimension. And in addition to a single mode Bingham distribution, we have also tried fitting 2-mode Bingham mixture distribution. So basically, what we did is we take the distribution from 2 Bingham distribution and sum them up with some kind of weights. So in order to fit the distribution, even though there is a provable algorithm for the single mode case, there's not one yet for the second mode case, and the parameter space is pretty large. Meaning for a single mode distribution, it has 11 degrees of freedom, and for a second 2-mode distribution, it's like 23 degrees of freedom. And the additional one parameter came from the weighting parameter. So we did some kind of gradient descent to explore the loss landscape. So to initialize for the single mode distribution, I've surveyed 3,000 starting points in total. And to give you an idea of how I did it, so this is one step in generating the one type of this parameter. So basically, I'm sampling dots on a sphere, but they will be converted into S3 sphere, dots on the S3 sphere using some kind of vibration. And also, I'm also generating points on our R3 plane. And they basically do some combination, and then I can start the algorithm. And to present you with results, as we can see, there are many disks on this big sphere. So for each angle on the sphere, on a disk, on a small disk, it represents a rotation. So, which is just to give you a reminder, it's basically connecting the orientation of the first domain and the second domain. And so as we can see here, the red area represents a high probability and the white one represents lower probability. And to evaluate how well the distribution did, we can look at the some kind of metric for our experiment, which is called RMSD. And for this value, the lower is better. And I fit the 1 billion distribution to 2 sets of data. And for the first data, it got an RMSD of 10.8, and second, it's the RMSD of 3.2. So we can see that it's fitting not as good for the first set of data. And also we have generated second different kind of solution. However, this one did poorly compared to the previous one. As you can see, the RMSD is almost tripled in value from the previous one. So also we can validate our results by comparing our results with the published data. As we can see from Hashimi's lab, they have computed a discrete ensemble for this molecule that we are interested in. And as we can see, the bound angle is about the same. And we can do a more precise comparison by converting it to the Euler angle from the most probable rotation matrix. And the mode this orientation has a beta value of 54 degrees. And if we look at the published data from our Hashimi lab, and we are interested in the green data or tar data, and we can see it's about correct, because the median is about 54, as you can see on this graph. And we have also computed the result for 2-mode data, and they did not perform as good as the first one or the single mode data. So for future work, we will apply this method to more structures and also run more experiments for the 2-mode models. Also, we will run gradient descent that favors the first alignment and validate the current result through converting the discrete ensemble into a continuous distribution and then comparing them both. Finally, we'd like to find a provable algorithm for the 2-mode case. And thank you.